with some delay. And last time I introduced curly C, this ring of germs of continuous functions, and its subfields, which I called Hausdorff fields, and they are naturally ordered fields. And capital H will be a Hausdorff field till further notice. So, and then I stated this proposition, and I state it again in a little bit more slightly modified form. So
let's. Sorry.
Yes.
H field was Hardy field before, or something more or less.
No. H is now a Hausdorff. H is simply denotes a Hausdorff field.
So it's something new, and one should get rid of all the past associations.
Well, I defined last time Hausdorff fields as a subfield of curly C. There is no derivation here. I'm starting with something quite primitive, which is just an ordered field. It's not an H field or a Hardy field yet. There is no derivation present yet. But let me say that it is still a useful notion, because even when studying Hardy fields, sometimes in extending Hardy fields, you first show that it's a Hausdorff field and so on. So it is still a useful thing. But if you don't remember the definition of a Hausdorff field, yeah, I guess you have to look at the notes of the first lecture.
Okay, thanks.
Yeah, anyway, so let Py be an irreducible polynomial over my Hausdorff field H in one variable. And so the leading coefficient, the coefficients here are these germs, A0 up to AN, and AN is the leading coefficient, which is not 0. That means, of course, that AN is eventually either positive or eventually negative. Anyway, then eventually the following happens. If you plug in t, little t, then you get a polynomial over the reals. Yeah, an t y to the n, an minus 1t, capital Y to the n minus 1 t, etc. You get a polynomial over the reals, and this has exactly n distinct zeros. And all of them are non-singular, which means they are not zeros of the formal derivative with respect to y, which I denote as partial derivative, but it's just a formal derivative with respect to the y variable. That's the first part of the statement. And then the second part is that the real zeros are actually given by germs in curly C. There are y1 less than y2, etc. in curly C, such that for sufficiently large t, yeah, that's what this eventually means. For a large enough t, y1t, y2t, ydt are the real zeros of this polynomial. Okay, so maybe I should draw a picture to illustrate part 2. So you have here the t line, the t axis, and here the y axis, and then you have for sufficiently large t, you have these germs y1, y2, y3 here that give you the zeros of the polynomial capital P little ty. Right, and so now I have to start with the proof, and for one, now I have to get my notes. Oh. Okay, now we are going to exploit, of course, that P is irreducible. So that means that P and its derivative with respect to y are co-prime. So what that means that AP plus B partial P with respect to y equals 1 if A and B suitable polynomials also in HY. And that means that for big T, AT P, sorry, for big T, AT comma Y, P T comma Y plus B T comma Y partial P Y T comma Y is 1, which means that so P T comma Y and the partial derivative T comma Y have no common zero anywhere, let's say in C. Right. Yeah, so that proves part 1, right? Part 1 was saying for sufficiently large T, of course, this is exactly degree n because A and T will not be 0. And so there is no, and all the zeros have to be non-singular as we just saw. And so there have to be exactly n. And now I say that the number of real zeros are continuous functions of T, and they are separated in this way, y1t less than y2t, etc.
Lou, excuse me.
Yes.
What is the meaning of studying complex zeros of the polynomials which are inherently real?
That's what I want to show in improving part 2.
Well, okay.
Right. So for big T, so I'm not going to use quantifiers in the exact formal way. So when I say for big T, that means, of course, there exists some real number R such that for all T bigger than R, etc. Right? But I will just say for big T, for big enough T, that y1t less than y dt be the real zeros. Now, a priori, this might depend on T, this number of real zeros. But of course, we will see that it doesn't depend on T for big T. We have to show, among other things, we have to show that T, the number, does not depend on T for big enough T. And that these are continuous functions, y1t to y dt are continuous for big enough T. Well, let's just say at T. Yeah. And since T is arbitrary, this will mean that y1 and yd as functions of T are continuous. Okay. Now we introduce also the complex zeros. Yeah. And they of course appear in complex conjugate pairs. So u1t plus I v1t, and let me write underneath the complex conjugate UMT plus I VMT UMT minus I VMT be the other zeros, be the other zeros. Now here, of course, d plus 2m is exactly the degree of the polynomial, pty. So these are all the distinct y1 up to y dt are plus these 2m are exactly all the distinct zeros. And maybe I should draw a picture. Yeah, well, let's say we have well, this is an example where you have 3 real zeros and 4 complex zeros, right? And so what we are doing, we are putting little circles around each zero. Such that the circles are disjoint. The balls, maybe I should, let me see if I should write this. Take little balls, B1 up to BD. And then for the complex zeros, I BD plus 1. And then also the complex conjugates of the ball, BD plus M, BD plus M, centered at these zeros. Yeah, so B1 up to BD circle centered at the real zeros, Y1 up to YDT, and the other one centered at the non-real zeros. And such that they are disjoint, yeah, disjoint. And these complex, the balls that correspond to the non-real zeros should not touch the real line. Yeah, if BD plus 1, etc., not meeting, not having empty intersection with the real line. Now there is a something that is known as continuity of roots, right? If you change the coefficients of a polynomial very slightly, then also the roots of it, real and complex, only can change very slightly. So so then let me say it this way, then for t prime close enough to t, each ball will still contain a zero of p t prime comma y. Yeah, so I changed right. So yeah, I mean, this is, let me just call it continuity of roots. For example, in my book on theme, of course, this is very well known, but I happen to remember that in my book, Theme Topology on NO Minimal Structures, this is lemma 1.3 on page 32. Yeah. See, if you want to look it up there, it's 32 of my book of Theme Topology, etc. Wow. sure you can find it many places. But of course, that means that each of these balls can only contain one zero of pt prime y, because the total number of real zeros cannot change. And that also means that each of these real balls can only contain one zero. And that means that these zeros that in these real balls must remain real, because if they would not remain real, they would contain a complex conjugate pair. Yeah. So so B1 up to BD contain exactly one. I hope this argument is convincing. Contain exactly 1 0 of pt prime comma y, and so these zeros must be real, because these real balls centered at a point on the real axis, if they contain a non-real point, then the complex conjugate would also be in there, and that's would contradict that they contain exactly 1 0. Yeah. So what this shows, so that means that the number, and also these complex balls, the non-real balls, the zeros that lie in there will not be real, right? Because they don't touch the real, these balls do not meet the real line. And so that the number of real zeros stays the same, and the number of non-real zeros also stays the same. And so, and this also shows that these real zeros are continuous functions of t. Yeah, so the number of real zeros remains d, and y and yit prime and zeros and well, let me see, and real zeros and these zeros y1 t prime less than, they also maintain their order, t prime are continuous as functions, well, at t as when you view them as functions of t prime, functions of t prime. And of course, then the rest is a connectedness argument. Yeah, I mean, so this shows that locally around t, what I said in part 2 of the is correct. Yeah, for if I stay close to t, then oh, this is, I have to go back to the statement of the yeah, this would be correct if I stay close to t, but because of connectedness of the real line, what this local behavior remains valid globally, or for big enough t. Yeah, now use connectedness. Yeah, this is a little bit sketchy, maybe use connectedness, but certainly should not be a problem to make this completely precise. Connectedness to go from local behavior at t at any at big enough t to the global behavior described in part 2. Yeah. Well, okay. I think I'll stop the proof here. It's already a bit right. Okay, now one consequence I want to immediately draw, which is 134. If n is odd, yeah, if n odd, there must be at least one, then d is greater than equal to 1, right? Yeah, since we have d plus 2m equals n, if n is odd, then the d must be, there must be at least one real zero for t big enough, and this, and even given by a continuous function or continuous germ, an element of curly C. Okay, so now let me remind you of a definition, or remind you, I don't know, for some it might be the first time they see it, but an ordered field K is said to be real closed yeah, so that comes from this Artin-Schreier paper that I mentioned last time. If every positive element is a square, yeah, this is my notation for positive elements in an ordered field. I write this, wait, let me draw this a little bit better here. Is a square in K, and every odd degree polynomial polynomial py in ky has a 0 in k. Now, yeah. One remark, it's enough to consider odd degree polynomials that are irreducible, right? Because if you have an odd degree polynomial, then it must also have an irreducible factor that is odd degree. Anyway, in some sense, that is a kind of a moot point, because a real closed field is almost algebraically closed in the sense that equivalently, and here I have to rely on equivalently, if I adjoin I, you get something that's algebraically closed. I squared is -1 is algebraically closed. So algebraic, real closed is very close to algebraically closed. You just have to join the square root of -1. Yeah. And of course, this is also important in the history of model theory, since Tarski proved that all real closed fields, ordered fields, are elementarily equivalent to the real field. They have exactly the same elementary properties. And okay, so now I can state theorem 135, and let me in a way it's implicit in Hausdorff, this paper that I mentioned, and more explicit in Bojanitson's paper that I also mentioned. Although in both cases the statement is a little, it's not exactly the same as what I'm saying. Bose-Nissan only considers Hausdorff fields that contain all the real numbers, and Hausdorff considers really not so much germs of continuous functions, but sequences, germs of sequences of real numbers. Anyway, H, our Hausdorff field, has an algebraically closed, has an algebraic extension, algebraic real closed Hausdorff field extension. Field extension, which I will write as HRC, standing for the real closure. And it's actually unique in a strong way for any such HRC. We have that it's equal to, let me call this star, HRC is all the germs, all the elements in curly C that satisfy a polynomial equation over H. Non-zero polynomial. Yeah, so in other words, this in particular means that HRC is uniquely determined by H. Uniquely. And we call it the Hausdorff real closure, if you want, or the real closure of H as a Hausdorff field, uniquely determined by H, right? Because that's what this equality tells you. And now, from what we did, this is pretty easy. Yeah, the first part, that you have an algebraic real closed Hausdorff field extension, is, well, you just keep adjoining square roots and roots of odd degree polynomials or irreducible odd degree polynomials till you can't do it anymore, right? Till you have exhausted. Yeah, you go, or you can use Zorn. You say you go to a maximal algebraic Hausdorff field extension, and that will automatically have the property that it's real closed, because if it weren't, you would have to be able to join a square root, and then it wouldn't have been maximal, or you would have been able to join a root of an odd degree polynomial, but you can always assume irreducible. So proof, the first part, as I just explained, is clear from what we said about joining square roots to Hausdorff fields, square root of f for f in H, yeah, to any Hausdorff field, and from the proposition that we just proved, 1, 3, 3. And now I have to prove this uniqueness in this form star, right? So let HRC be as in the first part. And I have to show that it's yeah, we show star. Well, well, one direction is clear. Holds because I'm assuming that HRC is algebraic and an algebraic extension, and so every element of it must be a zero of a polynomial over H. Holds because HRC algebraic over H, right? And the other direction, yeah, well, HRC is real closed, and that means that yeah, so let y in HRC say py, and then it must be algebraic. So say so py is 0, p in hy, non-zero hy. Oh wait, what am I? Sorry, I'm confusing myself. Let me get. What I have to assume is let y be an element of curly C. Yeah. I start with an element of curly C, and I have to erase more curly C, and suppose it satisfies an equation, a non-trivial polynomial equation over H. What I have to show is that y is then actually in to show y is in capital HRC. Yeah. Keep in mind, I have a little y here and a big Y. I usually use big letters for indeterminates, and little letters for the things that I'm substituting for them. Okay, so now HRC is real close. That means that this polynomial can be factored as follows. We have py is, well, some element of H with times y minus y1 to the power e1, y minus yd to the power ed, times some product of quadratic irreducibles, right? I mean, this of course is a well-known fact about the real field, but it's true for any real closed fields. So it's a product of linear factors times the product of quadratic irreducibles, which look like this: y plus bj squared plus cj squared, where yeah, so first of all, a should be an element of a is not 0, and y1 up to, yeah, bj, all the bj and cj are in H. Cj should be non-zero because I want this to be irreducible over H. And y1 are elements, are the real roots ordered in according to the ordering of H. Okay, but then little y, if you plug in t big enough, yeah, pty, you will see that little y must equal for every t, one of the yits. Yeah. Then for big T, yt equals. Oh yeah, I forgot to say the exponents e1 up to ed here should be positive natural numbers, right? But for big T, yt has to be yit, but it cannot jump from one yit to another yit, since the y's are continuous and y itself is continuous, and the y's, the y1 and 2 yd are do not cross each other. So for yt is yit, independent with I, independent of t. For big enough t, right? And that means that y is IE. So y is yi in h, in the real closure. Okay, so that is the proof of this theorem.
Now,
Yes.
sorry, just a question. Y1 and 2yd are in H or in HRC?
Ah, you're right. Sorry. Yeah, thanks. They are in the real closure, of course. I factor, right. Yes. Okay, let me state a corollary here. 1, 3, 6. HRC is the unique real closed algebraic Hausdorff field extension of H. There is no other one, Hausdorff field extension. And note, everything is taking place within this ambient ring curly C. So, and let me also add something, but that for every, you might wonder, can an element in this real closure be much bigger than everything in H? No, that cannot happen. That for every germ in this real closure, there is an H, there is a little h in big H, such that y is in absolute value less than or equal to H. And this last thing is just a special factor, special case of a fact about any ordered field. Yeah. Let me for the second. Maybe I'll give the second part. Use that for any ordered fields. And I could leave this as I could leave this statement as an exercise, or you can look it up in many places for so for any ordered field K and any Y, any Y in any ordered field extension. Of course, that means that the ordering is also of K is extended to the extends to the ordering of the extension you're talking about. Any ordered field extension which satisfies, let us say, a n minus 1 y to the n minus 1 plus a 0 is 0. Yeah, all a y, all the coefficients in K. We must have the following estimate is less than or equal to 1 plus the maximum of the absolute values of the coefficients. 0 less than I. Yeah, so consider this as an exercise if you want. It's quite easy. But one mistake that sometimes is being made is that people think that therefore, because of this, that every element in the real closure must be less than something in the original ordered field, that means that capital H is dense in the order topology in its real closure. But that doesn't follow, and it's not true. There are counterexamples. And it's also it's a source of mistakes that sometimes people make. And you can try to find your own counterexample to that statement. Okay, so maybe I will also add one of the things that Hausdorff was particularly interested in, 137. Maximal Hausdorff fields are, because of John, there are maximal Hausdorff fields. You know, every Hausdorff field extends to a maximal one. They have to be real closed. Hausdorff fields are real closed. Right, yeah, so in this paper that I already referred to, right, let me also put an exercise. I will come back to maximal Hausdorff fields again, but because Hausdorff had particular interest in those things. Exercise 138. Yeah, so let's make a small connection to O minimality here. Let's consider the usual ordered field of real numbers, which I denote this way. RL is the reals. Then with its ordering 0, 1, plus, minus, times. Yeah, the usual ordered field of real numbers, which is O minimal. And so then last time I mentioned that if you have an O minimal expansion of the real field, and this is one of them, then you can form the corresponding Hausdorff field of definable germs of definable functions, right? And which so this is the Hausdorff field of germs of definable one variable functions. This is exactly the real closure of the field of rational functions. Yeah, inside the curly C. So yeah, this is okay. Good. 1 point. Let me see what is the time. It's yeah. I should go for 2 hours now, right? So smoothness. I want to. Yeah, it turns out most things that people are usually doing with Hardy fields, you can actually do already. Not most things, but a lot of things you can actually do in the setting of Hausdorff fields already. So one can already consider some smoothness issues in this setting, but some notation. Let R be a natural number or infinity. Then I introduce curly CR as the subring of curly C, consisting of the germs of R times continuously differentiable. Continuously, I would perhaps want to say of the germs of CR functions, but yeah, that sounds a bit circular. In terms of R times continuously differentiable real valued functions on intervals, on half lines, if you like, from A to plus infinity. Yeah. Right. So this makes sense for R a natural number, and also for if R equals to infinity. And yeah, so in particular, C0 is just C itself, right? And I also want to allow R to be omega, yeah, and C omega, where do I, yeah, wait a minute. Before I say that, let me say for R greater than or equal to 1, for R, well, let's say R a positive natural number, we have the derivation, but it's not a derivation on CR, it's a derivation from CR into the previous one, yeah, F prime from CR to CR minus 1. Yeah, you lose one derivative, one order of differentiability in general, but it does restricts to a derivation on the usual derivation of or on C infinity and on C omega, which is the same, right? Which I didn't define, but it's the same thing, is same as above, but with a real analytic instead of R times continuously differentiable. With real analytic. Of R times. Okay, I hope this is all. Oh, wait a minute. Let me see, where am I now? Yes. I want to say that I want to add something to my earlier proposition on continuous solutions of a polynomial equation. I want to upgrade this to the following proposition 1.4.1. Yeah, let R be yeah, a natural number, or it could also be infinity or omega. Yeah, and suppose again, my polynomial as before is irreducible, but now I'm assuming that the coefficient functions or coefficient germs are CR, irreducible with all AI in CR. Then these real zeros, then the Y1 up to YD from that I started out with today from proposition 1332 are also in CR, are also in CR. So they are not just continuous germs of continuous function, but germs of CR functions. And this is basically the implicit function theorem for y equals yi. We have, well, pt yt is 0 and partial p y t comma yt not 0 for big enough t. As we saw in part 1 of that t, then implicit function theorem says that locally these functions y must be of class CR, and of course that means for all big enough t gives y in CR. Right, so yeah, implicit, this is my abbreviation for the implicit function theorem. And yeah, this implicit function theorem is true in all these classes CR and C omega and C infinity. Okay, yeah, if there are any questions, let me know. But this has a corollary that's will be useful in the Hardy field setting also for R is above. If the whole H is contained in CR, then its real closure is contained in CR as well, right? Because the elements of HRC will be actually right. The way we constructed HRC by adjoining solutions of these irreducible equations all the time, this being in CR is preserved. Okay. Yeah, and for later use, it's actually useful to have an explicit expression for the derivative of such a root. So for later use, we note that for Py y equals yi, as in what was it, the statement of this proposition here in 1 for 1, and r greater than or equal to 1. Oh yeah, I said use the implicit function theorem. Of course, this only really makes sense if r is greater than or equal to 1, but for r is 0, we already know this, right? So this proposition was right. And r greater than to 1, we have an explicit formula for y prime as follows. We have a n t y yt to the power n plus a n minus 1 t yt to the power n minus 1 plus a 0 t 0 for big enough t, and take derivatives. Take the derivative with respect to t in both sides. Take derivatives to get well, let's say if you first if you use the product rule for each of the terms, you get summation I is 0 up to n ai prime t yt to the power n plus, and then summation I is let me see, 1 up to n I ait yt to the power n minus 1. Oh, and this whole thing multiplied by y prime t equals 0. And now this is simply this partial p with respect to y t comma y t. And we know that this is not 0 because we are talking about non-singular. This is not 0 for big enough t. So that means we have y prime t equals minus I is 0 up to n ai prime t yt. This is in a way a differential equation for y, right? Divided by partial p. Wait, I did. Yeah, you can think of this as a differential equation for y. Y prime is on the left and y appears on the right. And this will, let me put when we talk about Hardy fields, this will again play a role. Right. Okay. Yeah, so now I go to the next subsection, but if there are any questions, please interrupt.
Lau?
Yeah.
So maybe you are going to say this later. So, but do you expect that these maximal fields are isomorphic for different R's?
They are going to be back in, well, they are basically what Hausdorff proved in this paper is that they are back and forth equivalent. I don't think it's known whether they are isomorphic. I mean, they are isomorphic, of course, if you assume the continuum hypothesis,
Right.
because they are back and forth equivalent, but I'm not sure it's known whether they are without that.
Okay. But even for different R's, they are back and forth equivalent. For
what do you mean by for different R's? Oh,
the maximal C2 field is back and forth equivalent to the maximal C1 field.
Well, I haven't. I'm not sure about that. What I said was just about maximal Hausdorff fields. So I haven't thought of adding the smoothness conditions to, and then considering maximal things within this smoothness classes that but yes, that's a good question. I'm not sure.
Okay.
Adjoining. Yeah, now adjoining transcendental germs. Adjoining germs. Lemma. Yeah, so this is a nice lemma. And here we are, by the way, because of our real closure operation, for many problems, you can just assume that your Hausdorff field is real closed, or later on Hardy field is real closed. And because often one can reduce to that case. So suppose H is real closed. I'm still working with my given Hausdorff field, capital H, and Y C is such that for all H and H, Y, the difference is a unit. Yeah, that means that eventually Y is bigger than H, or eventually Y is smaller than H, right? Because the units of C are those terms that are eventually positive or eventually negative. So that's a strong assumption of, well, a reasonably strong assumption, but it's much weaker than what seems then the naive assumption that you want to, that is needed to join Y. I want, yeah, then Y generates a Hausdorff field. Y generates over H, Hausdorff field extension H Y of H. Right, because for right. For that you have to check not just differences, but polynomials in Y have to be non-trivial polynomials in Y have to be units. Okay, but the proof is now quite easy. So let's consider a non-zero polynomial over H. And then we factor it again. So P Y is A times, well, H1. I don't care whether the H's are all different from each other. It doesn't matter. And then the product of the quadratic irreducibles, Y plus BJ square plus CJ square with A in H1 up to HD, and the BJs and the CJs are all in yes, in H, CJ not 0, to make it really irreducible here. Okay, then what is, if we plug in PY, we just get a unit, right? Because the A is a unit, since it's in this non-zero element of this Hausdorff field, and then Y minus H1 is a unit by assumption. Y minus HD is a unit, and then the product of all the little y plus bj square. Well, since these are positive ultimately, eventually, they are all units. So this is in C. So that means that we have proved that the whole ring generated by y, little y, consists of units. Well, the non-zero elements in here are units. And that's it. Now we just apply this lemma, which says if you have a subring of C whose non-zero elements consist of units, then you can form the fraction field and you have get a Hausdorff field. Yeah. So get Hausdorff fields. Yeah. Okay, and I want to use this now. Let me see. Yeah, I want to use this now to prove something that is usually done only in the context of Hardy fields, but one can already do it in this setting. Basically, it says that you can join logarithms, provided you have sufficient smoothness. Yeah, so there's one, this is, let me see, this was 151. Yeah, and corollary 152. Suppose R is contained in H. Yeah, so now I make this extra assumption that all the real numbers are in H, which Bose-Einstein automatically does, but and I also assume that all the functions, all the germs are C1. Yeah. And I have a germ, which is C1, with derivative in H. Y in C1 satisfies Y. Yeah, so basically I integrate some function in H. Well, let me call it F, this derivative. Equals. In other words, I take an element in H and I integrate and I get some germ in C1. Then I can join this to H and still get a Hardy field, a Hausdorff field. Then Y generates Hausdorff field extending Hausdorff field. Let me just write H, Y. And this is a nice application, I think, of this general lemma here. Well, first of all, we can reduce to the case that H is real closed. Yeah. Right, because otherwise you just pass to the real closure. H real closed. And also that Y itself is not yet in H. Yeah. And Y not, if it's already in H or in it, then of course we are done. Right. So what I have to show now is that if I compare Y with an arbitrary element of H, enough to show that it's enough to show by the lemma that the difference is a unit. Yeah, in other words, the in the ambient ring. Yeah, in other words, Y is eventually bigger than H or eventually less than H. But suppose this is not the case. Yeah, suppose Y minus H not in the unit. Well, that means that for arbitrarily large T, it will be 0. Yeah. Suppose then, right? If Y is not eventually positive nor eventually negative, well, that it means it must have arbitrarily large zeros. You know? So then YT equals HT for arbitrarily large. There's a sequence of T's that goes to infinity where this happens. And then by Rolle, so between any two T's, big T's, where you have yt is ht, there will also be a t in between where the derivative y prime t equals h prime t. Yeah. So y prime t, not the same t's, of course, but for arbitrarily large t, yeah, because i.e. so, but what y prime was simply f, right? So f t is h prime t for arbitrarily large t. But f, and now we are in h, f is an element of h prime. Wait a minute now. Did I make, I think, oh, no, wait, what am I saying here? ft is x, what am I have, yeah, and now I think I made a mistake. I have to assume that h is actually closed under, you see, what I want to use now is that f(h) prime is, little h prime is also in h, but that's not part of the Hausdorff field axioms. Let me see, how could I have overlooked this? Y prime. Right. Yes. So maybe I should say, I should add to the assumption that H is, well, what amounts to saying that H is a Hardy field, namely closed under taking derivatives, right? H and H, how shall I, let me write it this way, delta H contained in H. So delta is the, that means take the derivatives of the elements in capital H and assume that they are again in H. That's really the definition of a Hausdorff Hardy field. And if I, yes, that's strange that I overlooked this assumption anyway, but then I can get that f equals H prime, yeah? So f equals H prime, because then f and H prime are both elements in capital H, and so if they are equal for arbitrarily large t, then they must be equal as germs, yeah? So that means that y prime equals H prime, so y equals H plus a constant, a real constant. But the real constants were already in H, yeah? So this is an element of H, and I get, and that contradicts my assumption here that y is not in H, yeah? Yeah, sorry for this confusion. I really, anyway, that is right. It's now 10:15. Oh no, wait a minute, where it is no, it's 11:15, sorry. Yeah. Right. Good. So let me write down an extended exercise for the students and or for yourself if you like to do it. And part of this comes from a discussion with Ilyas Farah a few years ago. Well, first of all, that's if H is maximal as a Hausdorff field, So among Hausdorff fields, there are maximal ones. And then if you take limits, you get all the real numbers. Then R T where H is bounded. Yeah. In this. Right. And of course, note also that the intersection of H with R is real closed. Note. Yeah, I'm not saying that the maximal Hausdorff field contains the reals, but it contains, but if you take limits as t goes to infinity, you do get all the real numbers. H intersected with R, which might be smaller than R, is real closed. Yeah, because it's an intersection of two real closed fields, which is also real closed. 2, and this makes it quite clear that you get many situations where the reals are not included in the maximal Hausdorff fields for any real closed subfield E of R. There is a maximal H, maximal Hausdorff field, such that H intersected with R is exactly E. Right, so there are, yeah. Well, I mean, for the students, I'd be happy if you just did it for E, the field of real algebraic numbers. Yeah, just in a way that makes it clear that the proof works for any E. Just do the case. This is the smallest real closed subfield of R, real algebraic. Yeah, all the algebraic numbers, all the complex algebraic numbers that happen to be algebraic and real. Real algebraic. Okay. Yeah. So also 3, if you take the intersection of all maximal Hausdorff fields, you get something very small. It is exactly the real algebraic numbers, nothing more. Well, that's, if you do 2, then that will be pretty clear, I think. So this is a very different behavior, by the way, from Hardy fields. So Hausdorff fields are, in some sense, have features that you might consider as somewhat pathological, but now a consequence of 2 is that there are actually continuum 2 to the continuum many. There are an enormous number. 2 to the power continuum. I suppose maximal Hausdorff fields. Right, and 5, and that is what Hausdorff was, where he invented his back and forth method for. Any 2 maximal Hausdorff fields are back and forth equivalents. Yeah, so this requires a little knowledge of model theory. Any 2 maximal Hausdorff fields. So that's a lot stronger than just saying that they are elementarily equivalent, which of course is a consequence of them being real closed and Tarski's theorem. Back and forth. Equivalence. And therefore isomorphic under the continuum hypothesis. Right. I mean, this is of course a little bit goes a bit too much in the set theoretic direction, but I thought it would be good to at least mention these things. Right. So there are there are two more items that I want to get done today. So that is subsection, but I'm still continuing in the Hausdorff field setting, and next week on Tuesday I will start with the Hardy field, which is much richer, and where there are less pathologies. You could consider some of these things as a bit pathological, like you know, that for every the maximal Hausdorff field intersects the reals just in some very small fields. You might consider slightly annoying. Of course, you could also just consider Hausdorff fields that contain already the reals, and then some of these statements have to be still go through, but under extra assumptions, which I will leave to you to figure out. 1.6, the canonical valuation. Yes, on H. Well, we already have that basically. So we have the subring of bounded elements of H. Yeah, which is another description, H in H, which are less than or equal to n in absolute value. By the way, if I write m and n, I always mean a natural number, right? For some m and n in my world are always natural numbers. So this is a convex subring, is a convex, right? Between any two elements of OH, the things in between are also in OH. It's a convex of H, and the smallest, yeah, the smallest. Because once you have the integers in your ring, then of course, if you take the convex hull of it, you get OH, the smallest such. And it's it follows that this is a local ring, yeah, therefore OH. Oh, well, first of all, I should say that it's a valuation ring. Is a valuation ring of H, which means, i.e., if an element in H is not in OH, its inverse is multiplicative inverse is in there, yeah. If F in H, F not in OH, then it's multiplicative inverse. Right, so a subring of a field with the property that every element of the field is in it, or its reciprocal is in it, that's called a valuation ring of the field. And this automatically induces a valuation on the field, which in this case is simply given by our dominant relation. Yeah, so, and yeah, let me first say that this evaluation ring is always a local ring. That's a consequence of being a evaluation ring. OH is a local ring. It has exactly one maximal ideal, and its maximal ideal consists of the infinitesimal, right? Yeah, think of OH as the bounded element of H with maximal ideal. The infinitesimals, little OH. Yeah, so you see that the notation is a bit, mimics a little bit the big O and little o notation of Landau. Big OH and little OH is all the H in H that are infinitesimal, or H in H such that H is less than 1 over n for all n positive. Okay, and for so now this can also be written this way. Yeah, F is dominated by G if and only if F is in a bounded element of H times G. You know, and which in turn is, if you can take the valuation corresponding to this valuation ring, this is also equivalent to the valuation of F is greater than or equal to the valuation of G for the valuation little v on H corresponding to this valuation ring. Again, this is only for those who know about valuations. But sometimes we really need a valuation to do computations, right? Because VF actually takes values in an ordered abelian group, so you can add and so on. And this likewise is but yeah, of course, sometimes it's a bit confusing that there is a kind of reversal. Here you have F dominated by G written in a way that suggests less than or equal to, and here you have greater than or equal to. That's how traditional notation in valuation theory works. Oh, this is not 100% true, right? F is strictly dominated by G, requires G to be non-zero, you know, and G not zero, right? So unlike in curly C, you always have F is dominated by G, or G is dominated by F, right? That doesn't hold for any two elements of curly C, but for elements in a Hausdorff field, you have this totality, F dominated by G or G dominated by F. Okay, so that is one more topic that I want to go through, and then I will stop, I think, because but this comes up a lot, composition. Also in the context of Hardy fields. So we want to let L be in C be eventually strictly increasing. And L, yeah, L is eventually greater than any real number. Right, so it goes to, in other words, it goes to infinity. LT goes to plus infinity as t goes to infinity. That's another way of writing this condition. But But then we can compose, we can sort of make a change of variables instead of, yeah, we can use L as a sort of new coordinate. Then for, and I will actually do this even in this extended, this complexified C. The composition makes sense. F composed with L in CI is given by, again, I do the usual abuse of notation or terminology. F composed with L, it's a germ, but I do as if it's a function, is F of LT, for T big, for big enough for eventually. Yeah, let me write it this way, eventually. Again, it doesn't make any difference with which representatives you take, you always end up with the same germ. And this gives you the map F goes to F composed with L from CI to CI is an automorphism. Of the C algebra, if you like. Constants go to constants, to the same constants, complex constants, CI. And it also respects, it maps C, of course, to itself, maps C onto C, and respects the asymptotic relations. In both directions. Yeah, F dominated by G if and only if F composed with L dominated by G composed with L. All these things are very easy to check. Yeah, the inverse, this is an automorphism, and it has, that means it has an inverse. The inverse is F composed with F, and then you just compose with the inverse of L, where L inf in C, the composition. Inverse of L is given by just what you think, L inf, it's the unique element in C, which when composed with L gives you X, the germ of the identity function. And then L inf is also strictly increasing eventually. Then L inf is also eventually strictly increasing and strictly and bigger than every real number, strictly eventually strictly increasing. Right. Yeah. Notes. F composed with F composed with L, when you restrict it to C, it also respects the partial ordering, of course, in both directions. And it maps Hausdorff fields onto Hausdorff fields, both directions. And it's composed with L. Yeah, if you compose every element of a capital H with L, you get again a Hausdorff fields. Hausdorff fields. I mean, it's rather obvious from the earlier statements because this is an automorphism of the C algebra. It maps a subfield automatically onto a subfield. Right. And moreover, if you have some smoothness, H contained in CR, and L is also the same degree of smoothness, then of course H composed with L. And L inf, yeah, well, I think people know that if you take a compositional inverse of a CR function, it's again a CR function. Right. Okay, well, I think I will stop here. I mean, this last material is rather simple, but I just wanted to state it, and the verifications are really obvious, I think. Anyway, if there are any questions.
So do you know what happens if you put composition in the language? Do you still have back and forth equivalence?
No, I don't, let me see. I don't think so. Yeah, I mean, these maximal Hausdorff fields are probably, oh yeah, well, the thing is, if you take a maximal Hausdorff field and compose it with your little L, you get again a maximal Hausdorff field, but it will in general be a different one. Right? Yes, it will. In fact, maybe you can even show that it is always a different one. Well, not if L is the germ of the identity, but oh, I also have a sign saying that my battery is low. But anyway, yeah, no, I don't know. I haven't really thought about it, but except what I just said, that if you compose a maximal Hausdorff field with little L, it will be maximal again for obvious reasons, but not, but a very different one in general.
Okay.
Yeah. Any other questions?
Now,
Yes.
you mentioned the intersection of all maximal Hardy field, Hausdorff fields, which is just the field of algebraic numbers. But what about the intersection of all maximal Hardy fields?
Yeah, I'm going to talk about that. The maximal, the intersection of all maximal Hardy fields is a big extension of the reals. I mean, it certainly behaves quite different in the Hardy field case. In fact, it will be Liouville closed and closed under various things. And there are interesting open questions about that intersection, the intersection of all maximal Hardy fields. Yeah, that's an interesting thing that was studied by Bojanitsan a lot, and he was able to say plenty of things. And we actually can answer a few of his questions about it. I hope to get to that.
Okay. Thanks.
Anything else? Okay, well, then I think
one last question. So this intersection of all maximal Hardy fields, will it be a minimal? Or will generate a minimal?
this is one of my, I would conjecture, yes, I think that is an interesting conjecture, that all the things that are in all maximal Hardy fields must be so special that they should be generate an O minimal expansion of the real field. That's, I think that's an interesting open question, yeah.
Right.
Which I wanted to pose, but you did it before.
So can you go back to the lemma on adjoining integrals to?
Yeah, this one, right. Yeah.
So how do you get y prime equals h prime in the proof?
Well, let me see. Y prime was f, right? Okay. You see, in the assumption here, y prime is f in h, and I already have f equals h prime. So that means I get y prime is h prime. But maybe your question is, why do you get f is h prime?
Yes, yes. Well, why do you get it for arbitrary large t? I mean, you get it for y and h. That's fine. But what about the derivatives? What do you get?
Well, f. Note that I added my the assumption that the derivatives of elements in H are also in H, right?
I see.
So since ft equals h prime t for arbitrarily large t, that can only happen for elements of a Hardy field if they are, or of a Hausdorff field, if they are equal eventually, right? Because they, so since you have ft is h prime t for arbitrarily large t, you must have, and since both of them are in H, they must be equal as germs.
I see, thanks.
So the statement could be that the extension of a Hardy field by antiderivative is also a Hardy field, right?
Yeah. Yes, I will
Okay.
come back to that in the context of Hardy fields, and I basically proved already the main fact about adding antiderivatives in this corollary, but I will still state it because for Hardy fields you don't actually need this to assume that R is a subfield of it,
Right.
which of because you can anyway.
Yeah. Okay.
Yeah.
So maybe the corollary could be false for a Hausdorff field.
Well, that's what I try to. Well,
it's an exercise for us, maybe.
I thought so originally, but then in the proof I noticed that I was tacitly assuming that h prime was an element of little h prime was an element of capital H, and that was or maybe okay, if you see an argument to avoid assuming that capital H is a Hardy field, yeah, please let me know.
Okay, so we have to think about it. Okay.
Okay, good.
Sorry again, but I'm not sure I understand the point again. So, I mean, from yt, I mean, y is not in H, right?
No, but y prime is.
Yeah, but so from yt equals ht frequently, I mean, for arbitrary large t, how do you go to y prime t equals h prime t frequently? That's why.
Wait, but wait, are you talking about the very last line?
No.
In the proof?
No, I'm talking about the fourth line.
Yes, third and fourth line. Yes.
Yt equals ht. Well, this is Rolle, right? If you have C1 functions that are equal at 2 points, T1 and T2, then the derivatives are equal at some intermediate point of the interval. Maybe I should say it this way: you have an infinite sequence. You have a sequence T1, T2, T3, which goes to infinity, where y prime equals h prime, and then between any tn and tn plus 1, you will have also a zero of their derivatives. Or
I see. So it's not the same t. I see.
no, for
Okay.
arbitrarily large t, and then for other arbitrarily large t, yes.
I see. Thanks.
Right. Good. Yeah. For arbitrarily large t, we call that a quantifier. So anyway, anything else? Yeah, 4 here is really an easy consequence of 2. You basically have to show that there are 2 to the continuum many real closed subfields of the real number. Right. Yeah, for 5, I mean, for the students who want to who take this course, who are not familiar with back and forth, well, they can just not do it. They can just learn about back and forth, or simply postpone it till they have learned about it, or leave it to someone who does know about it. Right. Okay. Well, then I think I will stop here, and we'll meet again on Tuesday. And I hope that things will then be set up in such a way that everything is smooth. Yeah. Okay. So how do I? Yeah.
Okay, thank you.
Bye.
Thank you.
Yes.
See you.
Bye.
Thank you.
How do I?
Bye.
I don't know how to get out of this. How?
Wait for the battery to.
No.
expire.
Oh, I see. Right. Yes. Yes. Okay. Good.
Okay,
Mikhail, can you stop the recording, or should I?